Welcome back to the session 2 of Introduction to Polymers. In this class, we are going to discuss what is meant by degree of polymerization, functionality of the polymers, and what are the types of polymers that is formed, along with the homopolymer, copolymer and their types. Last class, we were discussing what is a polymer. The process of polymer was found out by a scientist, Hermann Schrödinger. He found out the monomer are converted to polymers, and we saw two examples for natural, like polymers having a single reaction as well as multiple monomers undergoing reaction. So either a single monomer can undergo polymerization process, or also a multiple monomer can undergo polymerization process. Whatever that is around you, most of the materials they are polymers that you say, the objects that you see, the in day-to-day life, they are most of the materials are polymers. So studying about polymers, their bonding nature and other things are very important. This class we will see what is degree of polymerization. So in the recap, I have told you that monomers form polymers, and this process of conversion to monomer to polymer was identified by the scientist Hermann Schrödinger, and also applications of polymers can be known. We saw polymers, monomers and polymers may be of two types. It may occur in nature as well as they may be synthetic. So natural and synthetic both are available. So this is what we saw in session 1. So in session 2, we are going to discuss about degree of polymerization. I told you, let us take the simple reaction CH2 double bond CH2. The same example we have seen in the last class. So ethylene forming polyethylene by addition polymerization, CH2 single bond CH2 N times. So this is nothing but polyethylene. So this N, the number of repeating units in a polymer, is known as degree of polymerization. So this N is known as degree of polymerization. So it is nothing but the number of repeating units in a polymer chain. In some cases, this term may be used to express the number of monomer units also. So this may indicate the number of monomer units. You can see how many monomer units are present directly in, but this is only in some cases. If you are using, as we seen in the example of formation of nylon 6,6, where two different monomers are used, this is not applicable. But in some cases, it directly denotes the number of monomers that is used. However, this is applicable only to the repeating units that consist of a single type of monomer. It is usually denoted by the letter N, and the generalized formula that can be given is Mn, where M is the repeating unit. So here M is CH2 single bond CH2, and N, it depends on the type of polymer. It may be LDPE or HDPE. So whether it is an oligopolymer or high polymer. So depending on that, the N value will vary. Okay, so this is about degree of polymerization. So degree of polymerization of the monomer ethylene, we saw it here. Ethylene can be on addition polymerization, it is converted to polyethylene, and this is your degree of polymerization. N is the degree of polymerization. So monomers with low degree of polymerization is called as oligopolymers. OLIGO, oligopolymers, and monomers with high degree of polymerization is called as high polymers. Here the molecular weight ranges between 500 to 5,000 and here it is between 10,000 to 20,000. Okay, high polymers. In the case of high polymers, it is 10,000 to 20,000. Now, let us see how to calculate it. How to calculate degree of polymerization. A polymer sample usually consists of distribution of chains with different degrees of polymerization. Therefore, an average value must be taken while determining the dP, which is a degree of polymerization. While determining this dP, you can take the average value. The degree of polymerization can be calculated by using this formula where dP is equal to m by m naught, where m is the molecular weight of polymer. And m naught is the formula weight of repeating unit or molecular weight of monomer. Formula weight of repeating unit m naught, and dP is nothing but degree of polymerization. So, a simple substitution, let us see. Problem 1. Let us take the problem as calculate degree of polymerization of a sample of polyethylene, PE, I am writing it as PE, polyethylene having molecular weight of 150,000 gram per mole. You assume this is the question. So, you have to calculate the degree of polymerization. What is the formula for degree of polymerization? dP is equal to m by m naught. So, this is the formula that has to be taken into account. So, degree of polymerization, in order to calculate the degree of polymerization, you have to know m and m naught. What is m naught here? M naught is the formula weight of repeating unit. So, you have to know what is the repeating unit. In the case of the polymer that is given is polyethylene. So, let us write the reaction CH2 double bond CH2 giving CH2 n times. So, the repeating unit here is CH2. What will be m naught then? So, m naught of repeating unit of polyethylene is equal to, you have CH2 single bond CH2. Therefore, how many carbon atoms are there? There are 2 carbon atoms and atomic number is 6, 12. The atomic mass is 12. So, what I am writing is 12 into 2, as there are 2 carbon atoms, which is equal to 24, and you have 4 hydrogen atoms. So, 1 into 4, which is equal to 4. Totally you have 28. So, m naught value is 28. dP is equal to, what is m? M is given here. The molecular weight of polyethylene, it is 150,000 gram per mole divided by, what is m naught? It is 28 gram per mole. So, which is equal to, on calculation you get it as 5.35 into 10 power 3 with no units. So, dP doesn't have any unit. So, this is how you will calculate the molecular weight, the degree of polymerization using molecular weight of the monomer, the repeating unit, as well as the polymer. So, this is, can you write another example? Problem 2. I am giving you only the problem. I want you to calculate the answer. Calculate degree of polymerization if molecular weight of tetrafluoroethylene, polytetrafluoroethylene is 120,000. gram per mole. Can you please find out the answer for this? You have to calculate the degree of polymerization. You have to write the polymerization reaction for polytetrafluoroethylene and then calculate, see what is the repeating unit, calculate the problem. So, tetrafluoroethylene is CF2 double bond CF2. I am just writing the reaction alone for you. So, you calculate this CF2 single bond CF2 n times. So, you calculate the molecular weight here as well as m is given in the problem. Just calculate the molecular weight, substitute it in the formula and find out what is the answer. You also have two other formulas, which is number average molecular weight. Number average molecular weight, it is nothing but Mn is equal to summation of Xi Mi, where Mn is the number average molecular weight and Xi is the fraction of total number of chains within the range. Fraction of total number of chains within the range, and Mi is the molecular weight of each size of polymer chains. So, Mn is equal to sigma or summation of Xi Mi. This is the formula for number average molecular weight, and weight average molecular weight is another term that is used. Weight average molecular weight is nothing but Mn, which is weight average molecular weight, is equal to summation of Fi Mi, where Fi is the weight of fraction of polymer chains and Mi is the molecular weight. Again the same thing, molecular weight of each size of the polymer chain. So, this is the formula to calculate the number average and weight average molecular weights. So, coming to the degree of polymerization, you can have degree of polymerization is nothing but when you take ethylene conversion to polyethylene, the number of repeating units in a monomer chain, in a polymer chain, is termed to be the degree of polymerization, and it is mostly the similar to some of the monomers with the some of the polymer and monomer, they have the similar repeat unit, and in some cases it is not. And you can have can calculate the degree of polymerization by using the formula dP is equal to m by m naught, where m is the molecular weight of the polymer and m naught is the formula weight of the repeating unit. So, we calculated I gave you two examples here, and I gave you the formula for number average molecular weight and weight average molecular weight here. So, coming to the functionality of the polymers, the number of reactive sites or bonding sites or even polymerizable groups that is present in a monomer is called as functionality of the polymers. So, why do you take this functionality as the important one? Because whatever the functionality, the polymer will be formed. But may be bifunctional, trifunctional and so on. Let us see with these examples. Let us take the monomer ethylene, CH2 double bond CH2. So, first example that you are taking is ethylene, and this it is bifunctional in nature because it has a double bond and there is distribution of electrons here. Therefore, they are bifunctional in nature. Second example that we are going to see is hexamethylene diamine, CH2 6 times NH2 NH2. If you see, it has two polymerizable amine groups. Therefore, this is also bifunctional in nature. Let us take the third example, glycerol. Glycerol, it is nothing but CH2OH, CHOH and CH2OH. So, this is glycerol, and this glycerol, it has 3 OH groups. Therefore, it is trifunctional in nature. So, the functionality depends upon the number of reactive sites, number of bonding sites or the polymerizable groups like this that is present in the monomer. Functionality decides how a polymer is formed. The functionality will decide whether a polymer may be linear, branched, cross-linked or network structure. If the functionality is 2, let us take a bifunctional species. If this functionality is 2, then it will form linear polymers. Straight chain polymers will be produced. I am drawing the structure here. Assume all these are the monomers. Linear polymers like this will be formed. So, this is a monomer, and again you can have other monomer also. Next, monomer chain. You have this monomer chain and all these are linked together, and here you can see the chain formation by covalent bonds. You can see the chain formation by means of the covalent bonds. This is a monomer. This into represents carbon. Cross, it represents carbon. So, chain formation by covalent bonds, and here each and every chain, it is linked by means of secondary van der Waals forces. And you can see these are bifunctional monomer units. So, this is an example how a polymer is formed in a bifunctional species. You can see the weak van der Waals forces and the primary bond, which is the covalent bond. This is the primary bond and this is the secondary bond that is formed. Each monomeric unit in the linear chain, it is held together by means of strong covalent bond of attraction, as well as the different chains are connected together by means of weak van der Waals forces, which are secondary in nature. Therefore, as the chains are held together by the weak forces, there is no restriction in movement of chain. Movement of chain is easier, and therefore there is no movement, there is no restriction in the movement of chain. So, in this case, the polymer formed will be soft and flexible in nature, because the chains are movable in nature. Therefore, the polymer chains are soft and flexible. Sometimes there may be growth of side chains also. So, you can also get branched structure by this. So, they are called as branched chain polymers, and this is much more restricted. The movement is a little restricted compared to the first one in a branched structure. So, we saw a linear structure which is like this, and this linear structure, it is held together by weak forces of attraction. Then I told you in the same type you can get a branched structure also, like this. So this is nothing but a branched structure. Branch structure, whereas the movement here also there will be weak van der Waals forces of attraction, but the movement will be much more restricted than that of linear chain polymers. And let us see what will happen in the case of trifunctional. If it is trifunctional or mode, then you get cross-linked polymers. In the case of trifunctional, you have cross-linked polymers or network polymers will be formed. Cross-linked network polymers will be formed, and the strong covalent force will be between all these three. I will draw the cross-linked structure. Here you can see all the bonds here are covalent. Here also you have covalent bonds. Highly cross-linked structure, all the monomers are connected by means of strong bonds, and the primary bond, mainly all these are primary bond, therefore they are very strong. And the movement of the polymer chain is restricted. Restricted movement is there, therefore they have high strength, toughness, heat resistance, and is insoluble in most of the organic solvents. Therefore, cross-linked polymers, they have high strength. Network polymers are trifunctional, they are similar to this. You can write the network polymers like this. These are monomers. Here, I am indicating the monomers like this. Can see highly cross-linked structure, again they have the same physical properties like this. So this is network, this is your cross-linked polymers. So you have network cross-linked polymers here, and if you see functionality, the number of reactive sites or bonding sites or polymerizable groups is called as the functionality, and you have bifunctional or trifunctional or more functionality. Based on that you can form linear, branched, cross-linked or network polymers, and in a linear polymer the monomers are held together by means of covalent forces, whereas each monomer chain, it is held together by the weak van der Waals forces. The movement of chain is easy, therefore the polymers formed will be soft, flexible, and even side or branch chain polymers are formed, which has a higher property than that of linear chain polymers. Also, if that functionality is 3, cross-linked or network polymers may be formed, which has a restricted movement, high strength, toughness, polymers with high strength, toughness, heat resistance, and insoluble in organic solvents are obtained by this. So this is about the introduction to polymers. We have seen the introduction and the terminologies that is related to polymers so far from the notes. Okay, thank you.